In quantum mechanics, every student at some point struggles with these four terms: observable, operator, expectation value, eigenvalue. They sound related, they show up together frequently in quantum mechanics, but they do not mean the same thing. And that is why students often mix them up. So, in this two-part series, we will clear the confusion. This is the part one of the video where we will discuss the difference between observable and operator. In the part two, we will discuss the difference between expectation value and eigenvalue. In classical mechanics, things are straightforward. If you have a mass m moving with velocity v, you just multiply them and you get the linear momentum. Done. But in quantum world, things change. Take an electron revolving around a nucleus. It is not sitting at one precise location or moving with one precise velocity. Instead, it is described by a wave function which spreads out in space. So what will be the momentum here? Like classical mechanics, can we have a definite number? The answer is no, not directly. Instead, quantum mechanics forces us to think in terms of probabilities. So, how does quantum mechanics describe a particle if not by a single value, like in classical mechanics? It uses a wave function, usually written as psi, and it's a complex function. This wave function itself is not a probability, but something deeper, a probability amplitude. Let us consider a one-dimensional wave function, a real wave function. So this is the plot, and for this plot, we can get the square of mode of wave function. Now this mode square of wave function represents the probability distribution of finding the particle. If I multiply it by dx, it gives the probability of finding the particle in this interval dx. And if I integrate throughout the domain, that is the area under this curve, it gives the probability of finding the particle in the domain. This is the language of quantum mechanics. Not definite outcomes, but probability encoded in the wave function. But notice that even now, the wave function does not tell us the exact position of the particle. It only gives us the probability of finding it here or there. So the real question is, how do we extract physical quantities like position, momentum, energy from this wave function? For that, we need a mathematical framework. We just drew a 1D real wave function, but it is not always like this. The wave function is not just a curve drawn in ordinary space. To analyze it consistently, quantum mechanics is placed inside a special kind of mathematical space called the Hilbert space. In Hilbert space, the wave function is treated as a vector. Now, why do we need to place the wave function in Hilbert space instead of just treating like an ordinary function? Because this space has three crucial features: completeness, inner product, and normalization. With these three features, Hilbert space becomes the natural mathematical home of quantum mechanics. Now let us understand the three features of Hilbert space. First, the completeness. Think about an ordinary vector. In 3D space, you can represent any vector as a combination of the basis direction, that is I cap, j cap, and k cap. So this vector A, we can represent it like this, and we can write in the summation form like this. Quantum mechanics works the same way, but now instead of physical directions like I, j, and k cap, we have abstract basis inside the Hilbert space. Now, any quantum state can be represented by this basis states. So, completeness means that any possible wave function, no matter how complicated, we can always express as a sum over this basis states. So just like in geometry, you never run out of direction to build a vector. In quantum mechanics, you never run out of states to build a wave function. That is what completeness guarantees in Hilbert space. Now let us try to understand this inner product. In geometry, the dot product tells us the projection of one vector along the direction of another vector. Here in the dot product of A vector and B vector, if I divide it by the magnitude of A, I get the projection of B vector along the direction of A vector. We have a similar kind of operation in Hilbert space, and that is known as the inner product. But before going to inner product, let us get familiarized with the notation. Quantum state can be represented using the ket notation. And to form an inner product, we need something that can pair up with the ket. That is where the bra notation comes in. So for every ket notation, we have a bra notation which lives in the dual space inside the Hilbert space. Now, let us take the analogy from matrix multiplication to understand the inner product. So the bra notation is like a row vector and the ket notation is like a column vector. The inner product is defined like this, and if I do the matrix multiplication of the two, we get a single number. So when a bra meets a ket, we get an inner product and it gives a single number, and this is analogous to the dot product, which also gives a single scalar quantity. In the dot product, we discussed that it represents a projection of one vector along the other vector. Like that, the inner product also represents the projection of one state along the other state. There is also another interpretation in terms of probability, that is the inner product represents the probability of finding the system in the other state. In the case of continuous system, this inner product can be represented in the integral form like this. Now, if we take the inner product with self, then it should be finite, and such type of wave functions are known as square integrable wave function. And in quantum mechanics, we only consider the square integrable wave functions. And by introducing a constant, we can make this integral to be equal to 1. And this is known as normalization. And this normalization forces 100% probability of finding the particle in that domain. Now that we have built the mathematical home of quantum mechanics, that is Hilbert space, we are ready to connect to physics, because till now we have been talking only about probabilities and the projection of one state to another state. Physical quantities like momentum, energy, or position, they are known as observables. But how do we connect these observables to the wave function which is living in Hilbert space? That is where operator comes in. So the mathematical tools that represents physical observables in Hilbert space are the operators. Here on the left hand side, let me show you some mathematical operators that you are familiar with. That is the integration and the differentiation. If I represent this integration by an operator I, that is an integral operator, when it acts on a function, then we get the integration of that function. Similarly, for the differentiation, if I represent it with a d operator, when it acts on the function, we get the differentiation. So, when an operator acts on a function or a vector, it produces a new function or a vector. Similarly, in Hilbert space, when an operator acts on a quantum state, it gives a new quantum state. And this is happening in the Hilbert space. So, if we have an operator A corresponding to an observable A, when this A operator acts on a quantum state, we get a new quantum state. Please note here that Not all operators correspond to physical observable. For example, like the projection or evolution operator, they are purely mathematical tools. Here I'll show you some of the basic observables and their corresponding operators. The position, its operator is written like this, and for the linear momentum, the operator is written like this, and these are written in the case of position basis. And unlike the classical functions, the operator order matters, and this will depend whether the operator are commuting or not. What about the other observables like kinetic energy and angular momentum or the total energy? In general, most observables can be written as a function of x and p, and using that, using the expression of the position operator and the linear momentum operator, we can derive the operator x expression for other variables. For example, kinetic energy can be written as p squared by 2m, and by substituting the operator x expression of p, we can get the kinetic energy operator. Another example is the Hamiltonian of harmonic oscillator. So the Hamiltonian can be written as the sum of the kinetic energy and the potential energy. And by substituting the expression of x and p, we can get the Hamiltonian operator. Observables, they are real numbers. And these observables are represented by operators in Hilbert space. So when we do the measurement, it should guarantee real results. This forces the operators to be Hermitian. Now, what exactly this Hermitian property guarantees and how measurements appear in Hilbert space, this we will find out in the next part of the video, that is eigenvalue versus expectation value.